Cheers and colleagues and audience in the hall. It's my pleasure to present for you my book. My name is Evgeny Talantsev, and I'm presenting research in the classification of hydrogen-rich superconductors. So the story started in 1957 when Martin Cooper and Schrieffer introduced the famous equation where the divide change the primary parameter. It took about 11 years until Neil Ashcroft realized that because Tc is depends on the square of the mass of the ion of the metal. So the hydrogen, the lightest element in the universe, actually should have the highest transition temperature. And if metallic hydrogen will be metallized at high pressure, it should have potentially the highest transition temperature. So here, what at that stage, all people, all speakers jump to our time, but let's stay here and actually calculate, because Neil Ashcroft provided an estimate for divide temperature and for other parameters in that simple equation. And when I substituted in the BCS equation, I got 55 Kelvin. So we should be clear that at that time, 50 years ago, it was no any talks here about room temperatures to superconductivity. So at that, at one, if we look at that, the paper was published on Christmas Eve of 1968. About, say, 4 weeks after that, Vitaly Ginzburg, which is another great scientist in superconductivity, had made his prediction for the same topic and using actually the same methodology of the BCS theory. Actually, no any proper one exists still now for unconventional superconductivity still. So, and his prediction was 150 Kelvin. Again, we should point it out that no any mentioning of room temperature superconductivity is. And also, Vitaly Ginzburg mentioned the reference 43, which I was not able to locate, but where similar idea was also in preprint of 1968. Two great guys, unfortunately I can't pronounce the last name of the first author. They actually came to the very clear and very robust idea, which works now, which is that if it's a lot of hydrogen in the compound, it doesn't matter if it will be some additional heavy metal there. And it should work because high frequency phonons. And the way that idea, they synthesize the first and presumably actually the last superhydride at ambient pressure, which is thorium 4H15. And what was most puzzling about that they did not observe the isotope effect. Actually, they observed the absence of it. And a real breakdown in the field was done 6 years ago. Obviously, all audience know that. So, and when Michael Herinet's group, it shows that it's possible to jump up to above 200 Kelvin transition temperature. It took about 3 years to go to find next superhydride, which is lanthanum H10, and is new compounds for the slowest phase of hydrogen-rich thorium phases was discovered, and also was discovered recently ordinary hydrides. All of that condition temperature well above 250, 200. Out is that very important problem that all people in the field indicates transition temperature at the onset of it. However, we can define transition temperature in many ways. So most rigorous one is transition temperature defined as zero resistance, and that obviously the highest is at the onset of the transition. Another many problems associated with that new hydrogen-rich compounds, but another problem which I want to point it out that we actually do not have many experimental tools to study that. So if it's, for example, we cannot measure upper critical field, and why is that? If we use this theory and Ginsburg-Landau theory and simply substitute all values, we can find that upper ground state, upper critical field is actually proportional to that transition of the plane square. This means that if we compare these new superconductors with A15 superconductors, which obviously have transition to temperature nearly 20 Kelvin and new above 200, so we should expect that it will be difference in upper critical field by 100 times, and this is a real case. Here, I just draw a green line where the limit for top word facility we have in the laboratories to study, to apply magnetic field to samples, and it's obviously only small part of the full experimental curve can be explored by that technique. So we can use a similar story for all other hydrogen-rich medium temperature superconductors. It's very high magnetic field required to suppress superconductivity in that. So we can use some extrapolative model to extrapolate value at ground state, and most popular at the moment is an analytical approximation given by Baumgartner et al. For classical WHH model. So we will use that. We can mention that other model also was proposed by in the past one I proposed in say a couple of years ago for that specifically the source materials. So I keep the experimental data of the Hermes group for HCS for two pressure, and we will use that numbers on extrapolative numbers for the analysis. Here in this table you may see full list of the hydrogen-rich superconductors known at the moment in my feed to the model for the extrapolated DC2 not with values. If we plot it in a plot transition temperature versus upper critical field, we can find that surprisingly enough, if we feed the data to the power law, simple power law, this power law appears to be parabolic and quadratic, and it is which means that this equation are actually reasonably good approximation for what is going on. This immediately means that ratio, which is the ratio of the alpha to the Fermi velocity, is pretty much constant for all hydrogen from the very low one, where is our sodium 4H15 is up to all newly discovered one. And simple equation can be used for estimate some, I mean, it is the same universal Fermi velocity for the hydride. So the next one, it was the initial attempt to place that new superhydrides on a Uemura plot, where on the x-axis is the temperature and on the y-axis is the transition temperature. Uemura and co-authors, they found empirical law that if we place all superconductors, known superconductors, at that plot, that all well-known and practically important and etc. superconductors are in a very narrow band on this plot, and it is expanded by transition temperature orders, several orders of magnitude, starting from heavy fermions to all cuprates. So, and my initial guess was that if there is a certain point of widely accepted point of view that superhydride are electron phonon mediated superconductors, that it should be placed somewhere at this corner. And to place that superconductors in that plot, we need to understand and calculate the Fermi temperature for these materials. So this calculation is easy to derive from all known theory of the superconductivity and solid state physics, and also for effective mass of the charge carrier, I use a simplistic equation given by the Eliade. Based on that, we only need to either use electron phonon coupling constant calculated by first principle calculation, or either we can extract it from the resistive curve measured by in experiment. So by fit of the experimental data to block pre-Meissner equation, we can extract divide temperature, and from modified Macmillan equation we can deduce electron phonon coupling constant, and from that we can reasonably robust and accurate calculate the T Fermi. When I did it for that HTS, I cannot believe on my eye because I did it obviously on a piece of paper. And when I saw on that, I think I need some orders of magnitude for there, because that HTS is located just above Kubitska 223, and it is just on the same line of unconventional superconductor. It's just on top of that, because since then it was already discovered several other systems. I placed it place it more and more and more, and what is there, so it just nicely cover same area above operates here, and if it's lower transition temperature, same like in a tin hydride, it is still within that place, within this band, and also because sulfur hydride can be obtained without annealing of that. So it is placed exactly on the same under the YBCO. And what is important, it was mentioned today by Professor Takano, that oxygen is located just below that heavy fermions, near the heavy fermions. So it means that actually this straight line, this straight band, in that is actually it's what we should probably rely on it. So my acknowledgement to granting bodies, and this is my result. Thank you for, and sorry for that interruption at the beginning. It is isotope effect. So isotope effect, from my view, it was shown in the first paper by Mikhail Emelian's group and Alexander Drozdov papers. It was a compound made of sulfur and deuterium. So if we compare deuterium and hydrogen, its chemical activities at such high temperatures, say 2000 centigrades, at such high pressure, which is saying huge, saying presumably at the formation of it or the phase growth, it's more than 200 GPa. It's catalytic activities of the hydrogen and deuterium is different, and it's not necessarily that this shift on deuterium samples actually appear from the isotope effect. So
okay,
it can be
so you say that this isotope effect might be not intrinsic.
Yes, indeed, Alexander. Yes, it is. So more important that in lanthanum system, Mikhail Emelian definitely shows that lanthanum H10, and when they made synthesis of that lanthanum dysprosium, lanthanum deuterium E11. So it's different composition of that, arrangement of that. Thank you for the question.
So your claim is that this is unconventional
superconductor? I just presented experimental data. Nothing personal, business, just business. So I placed it there. So somehow it's there.
Okay.
So it's just at the given value.
Okay, let's switch to the next question. So Dr. Denis, please.
May I have some comment to Evgeny? I'm sorry, but you have estimates for the metallic hydrogen that it BCS formula it may have the TC of 15.5 Kelvin, but you have nothing to do with BCS formula because this. If it is realized, it should be very strong coupled superconductor, and you must deal with Eliashberg equation. And Ashcroft's estimates are for room temperature superconductivity because it's a very strong coupled superconductor, and also superhydrides are also very strong coupled superconductors. This is a comment, and in an hour I must have the presentation on this topic also in some an hour about the superconductivity in superhydrides, and I think that you cannot use this is estimates. They are based on the simplest Fermi surface of superhydrides, but it's not so. This Fermi surface are more complicated. This is many, at least 3 bands in these superhydrides, and so it's maybe a more complicated case for so simple estimates. Sorry, this all my comments.
so much for your comment. So, yes, I clearly understand that now we understood that the electron coupling in hydrogen-rich superconductors. I just focusing now that at that time it wasn't that done. So, electron coupling here actually start to be considered, saying 4 or 5 decades later after that. So it wasn't at that time at all. So I just represent here 2 examples where people just gave that number. So I just want to show the evolution of that. So that people even cannot think about that it is possible. So they never claim that it's the room temperature. If you look at that Neil Ashcroft paper or Vitaly Ginzburg, so it's no any. So it was just simply happened now. Thank you for your comment. I will definitely join your talk and presentation and may ask questions too.
I think we were having questions. Is there still time for me?
Yeah, okay. So please.
Yeah, please. I'm quite delighted by this talk and also by Professor Shengelaya's question, because less than 2 years ago, I published a paper in which I put the hydrides on the exotic superconductor side by theoretical argument. And the argument, not to go into detail, was that sulfur is just 1 step below oxygen in the periodic table in the same column. And the analogy was by charge transfer between copper and oxygen in the cuprates and between sulfur and hydrogen in the hydrides. Okay. So there is definitely a theoretical argument that the hydrides should be on this plot where Professor Talantsev has put them.
Oh, cool. Thank you.
Yeah.